Hello. The videos in Unit 1 mainly deal with how to treat and report numbers properly. And now we've come to the crux of the unit, which is significant figures rules and what are exact numbers. By understanding these, that will help you avoid misrepresenting the reliability of your measurements and your data. For instance, in this calculation, let's just focus on one value, 16.1 milliliters. I've underlined the last digit from reading from left to right, the last digit that is meaningful, that tells us something about the quantity. I stopped at 1. Now, if I had more precise and calibrated glassware, I could have known what this digit is, and it could very well have been 0. But by stopping here, we cannot assume that this number is 16.1000000. Although when you put that in a calculator and press enter, it will say that it is equivalent to 16.1. But when you report those numbers, those are not the same. So the number of digits, or we're going to define this later, significant figures in your value, it represents how precise and reliable your measurements are. And my measurements for this number are reliable to the 10th digit. The 10th digit. Let us define some terms, and maybe that will help clarify this idea about significant figures. Okay. Let's give a little bit of a definition. In any reported measurement, all non-zeros and all zeros not used as placeholders. And we'll clarify that also as well. Used as placeholders are significant figures. Let's take a look at a value 0.00083 meters. All non-zeros, therefore 8 and 3 are significant, and all zeros not used as placeholders are significant. But these are placeholders. And what do I mean by placeholders? The only purpose for adding these zeros is to mark the decimal. We're going to go over some defined rules in just a bit, but I do want to give you a trick. If you express this in scientific notation, you would say this is 8.3 times 10 to the what? 10 to the 1, 2, 3, 4, 10 to the minus 4, because you want to go smaller from 8.3. So there are your two significant figures. So both numbers represent only two significant figures, whether you express it as a decimal or express it as a scientific notation. And we'll just use the abbreviation sig figs. There are two sig figs. Before we get to the actual rules, let me just also jot down sig figs are important to the actual value. They mean something. See, these zeros do not mean anything. We could get rid of them when we express it as scientific notation, but we can't get rid of the 8 and the 3. To the value. The other second bullet point is they add certainty and reliability to the value. Or they add to the certainty. Reliability. To the value. I think we're ready. Let's jot down a couple of significant figures rules. The first one is 1. All non-zero digits and zeros in between non-zeros are significant. All the zeros in between non-zero digits, we're going to call those captive zeros. Captive? Yeah, we'll call them captive. They're in between two numbers. And we said they are significant. Very simple example. Oops. Very simple example. 24.0061. Going from left to right, non-zero, non-zero, significant. These are called captive zeros because they're in between two non-zero digits, and that's a non-zero digit. So I like to underline the last significant figure when you read it from the left. There are 1, 2, 3, 4, 5, 6. There are 6 sig figs. Okay, simple enough for rule number 1. Number 2, we have a new type of zero called leading zeros. Leading zeros are the ones that indicate where the decimal point is. These are placeholders. Okay, let me give you a decimal, a value less than 1. I personally always like to put 0 before if you have a number less than 1 expressed as a decimal. 0.07302. How many significant figures does this value have? Definitely 7. Oh, I don't want to underline those. Definitely 7 and 3 and 2 are significant. 0 here is captive, but see, these are called leading zeros, and they are not significant. They're just placeholders. These are leading. Okay. What do I want to put here? Not significant. The last significant figure in this number is 2. Okay, and we have how many? 4 sig figs. 7302. Leading zeros are not significant. What was the trick that we saw a minute ago? Expressed as scientific notation. 7.302 times 10 to the what? 1, 2. And we're getting smaller. 10 to the negative 2. Now do you see, by using scientific notation, we get rid of the leading zeros, okay? And we definitely see that we have 4 sig figs. So here we have 6, and here we have 4. The last one. This will have probably 2 parts, because the opposite of leading zeros are trailing zeros. Trailing zeros are significant. There's a purpose for them in reporting these zeros. There are a couple of rules now with trailing zeros. Let's take our example from the cover. What was it? It was 16.1 milliliters. 16.1. I stopped there. If you recall from the cover, let's take a quick peek at that. See, I stopped at 0.1. I stopped at the 1. I didn't go further and add zeros because when I took this measurement, I'm not sure whether that's a 0 or not. That's where the error comes, in the 100th place. But if I had put a 0 here, okay, there's a reason why I put it there, because I now know from my measurement that that 0 does exist. It's not 16.14, 16.12. My glassware was accurate enough that I know that it's 16.10. So that is significant. Heck, if I even have even more precise glassware and more precise instrumentation, I could go, 3 zeros. Now I know for certainty that this is pretty accurate, 16.1000. The idea that by adding zeros, I'm increasing the the certainty of this value means that those zeros are significant. This is the first time I'm going to underline the last digit and it being a 0. Those 3 zeros are significant. 1, 2, 3, 4, 5, 6. So there are a total of 6 sig figs. Does the trick with scientific notation that we did up here work? Since we know, or since we want to tell the audience that those zeros are real, that we are certain that those zeros exist, okay? I don't know if the fourth 0 exists. I don't know if it's 16.100002, 16.100007. I don't know that, but based on my glassware and my instrumentation, I know up to this 0. Well, when you do scientific notation, you have to indicate that by putting the zeros as well, because those, again, are significant. They add value, or they add reliability and certainty to the value, times 10 to the what? Well, now we have to convert 1.61000 to 16.100. So we move it to the right, 10 to the 1. Again, if we know that this is 6 sig figs, when we convert it to scientific notation, we have to indicate that there are 6 significant figures. And this number is more certain than if I had left these out. Okay. So again, this is correct. And let's compare it to 1.61 times 10 to the 1. On the calculator, those two are identical. But by leaving out the zeros and showing that we only have 3 sig figs, right, 1, 2, 3, we are less certain. So this is an indication to the audience that we are less certain about the digits after this one. Or we could say it's not as certain as 1.61000, even though they are identical in the eyes of the calculator. So that is a trailing 0. There's more. How do I show this? There's more to trailing zeros on the next page. Because we could also have a trailing 0 that's not after the decimal point. what do we do there? Are those really placeholders or not? So for instance, let's call this 3b. And let's amend this to 3a. 3a. Okay, 3b. How about trailing zeros before decimal? Actually, we should say before decimal and without decimal, because those rules are going to be a little bit different. 61, 0, 0, dot. Okay. By putting the decimal place there, we are saying that those zeros are significant, and we know that they are true, that they have been measured. This one has 4 sig figs. And let's do our trick with a scientific notation. Since that's 4 sig figs, our scientific notation has to indicate that we are certain about those 2 zeros. Now that's if there's a decimal, times 10 to the 3. Okay. But if there's no decimal, and you'll see this sometimes, we are not certain about this. And we said we are indicating that there's error in these 2 digits here. Okay, so there's a range centered around 6,100. Let's use our pink underline also. We have that. And here, our last significant figure is actually that one. So these trailing zeros do not count. They're only 2 sig figs. So before decimal, okay, they are significant. But without a decimal, okay, without a decimal, they are not significant. Then how would you do the scientific notation in this case? You would indicate that there are only 2 significant figures by only putting the 6 and the 0.1. Again, in the eyes of the calculator, these 2 numbers are identical, but one is more certain than the other. Okay. One more, just for practice. Again, 45, let's say 450.0. What about for this? That 0 is not captive, it's a trailing 0, but it's before the decimal, so that is significant. This is a trailing 0 after the decimal, and that's using this idea that there was a purpose, there was a reason why I added that 0 there. Okay, because I'm sure of it. Now, if I didn't add a 0, that value is still the same, but this value is representing a number that I'm less certain about. This number, even covering the decimal point, only has 2 sig figs. This number, which is identical in the eyes of the calculator, has 4 sig figs. And we would indicate that using scientific notation as such. 4.500 times 10 to the what? We have to get bigger, 10 to the 2. I think that's it for significant figures rules. The next thing is exact numbers. What's an exact number? And why is it important in the context of significant figures? Because for all of these numbers, at some point, we aren't sure what's after that last digit. I'm not 100% sure if the last digit after this 1 is 0, or 000, or however number zeros you have. But there are numbers that we know for a fact that its point is 0.000000000 to infinity. Exact numbers have infinite significant figures. How can that be? Well, let's say a proton. A proton cannot be divided into a half a proton. So there is no such thing as 0.572 protons. It has to be a whole number, in other words. So when I say that carbon has 6 protons, what do I really mean? I mean that's the same as 6.00000 to infinity protons. Is that super important? Maybe not in this video right now, but in the next video when we do calculations, we have to know the certainty of each number, because when we report the very last final answer, our final answer has to reflect the certainty of our numbers. And if we have 6 protons and there's an infinite number of significant figures, that number has no bearing on limiting the number of sig figs that your final answer should have. The final answer's sig figs will be based on some other number. Okay? So that's called an exact number. And we should say here 6 is exact. We could assume that it's 6.00000. Now, this could get a little bit tricky when we work with conversions, because if we want to convert, let's say, centimeters into inches, 257 centimeters. I'm trying to make a problem off the top of my head, times, and I want to convert it into inches. What was the trick? You set up your dimensional analysis, okay, to cancel out the units you want to cancel out. And when we look this up online, it says that 1 inch equals 2.54. Okay. When we do that calculation, 3.257 divided by 2.54. Let's get rid of the scientific notation. I have 1.2822. How long do I go? 8, 3, 4, 6, 5. Okay, that's ridiculous, because I'm saying that I have a certainty up to this digit here, whereas my values that I used to make that calculation are not as certain. Okay, but this is the tricky part. This number here, you assume it has infinity sig figs, because this value, this conversion is exact. When given a conversion, like on an exam, assume that it is exact, unless the professor tells you it's not. Okay? So the number of sig figs, and we're not going to do it in this video, that we should round this to is based off of not this number, but it's based off of this number. Okay? It's tricky because not all conversions are exact, but to make things simple for my class, I will tell you whether the conversion is not exact. If I don't, you assume that it is exact and has infinite sig figs. Let me show you some stuff on the web. For instance, if I'm converting liters to pint, do you see how when I put this on Google, it says the approximate result is 2.113? Okay, so this number here, 2.113, is not exact. I don't think even this number is exact. Okay, but what was the example that we use? We use inches and centimeters. You see, at least Google tells you whether you have something approximation, whether you have something that's rounded, or whether it's something that's exact. So this is the exact. It doesn't say approximate. All right, so that's sig figs. We will apply these significant figures rules when we do calculations. Here we did a multiplication and division. We're going to do subtraction and addition also in the next video.